So back when we were talking about the forces acting on current carrying conductors, what we saw was that if there is current flowing in a magnetic field, it experiences a force. But with EM induction, we are actually going to do the reverse process, which is that with a magnetic field, we will be exerting a force ourselves. So there will be some motion relative to the magnetic field, and then we'll see whether there is some EMF or some current which is being induced here. So let's say we have an apparatus as shown here. So this is a coil with some number of turns, as is also seen from the diagram. And on the lower part you have a sensitive galvanometer. And a galvanometer is not really used for reading currents. If you remember your AS electricity, then an ammeter is used for that. But a galvanometer is just used to show if some current is flowing or if it is not flowing. So it just indicates the presence of current as opposed to how much that current actually is. And let's also mark here some poles on this permanent magnet here. So this is a bar magnet that we have. So with the bar magnet in a position like this, where it's just kept outside the coil and it's not moving, what we'll see is that this galvanometer shows no deflections. So it shows a 0 value of the current here. So if this is the 0 mark, so it's just pointing at the 0 mark. So there is no current flowing in the coil right now with the bar magnet stationary. So no deflection with the bar magnet stationary outside the coil. So if you remember what we've talked about previously, so there will be a magnetic field around the bar magnet north to south, and that will also be there in the coil, but strangely enough this is not going to create any current, and we'll see when a current will be created. So no deflection with the bar magnet stationary outside the coil. So then when is a EMF or a current actually detected? So with the same apparatus as was also there previously, if we now try to move the magnet towards the coil and not even necessarily entering the coil, let's just say it's moved from some distance and it's brought near to the coil as the direction is shown by the arrow, then the galvanometer would show some deflection. So the galvanometer shows deflection when the magnet is moved towards the coil. And similarly, if we, after having brought it close, and if we again place it in that position, again there would be no deflection. But let's say that from this position, as is shown in the diagram, if we take the coil back again in the opposite direction, so if we are then taking the coil back like the magnet back like this, so then we're taking this away from the coil. So what we'll actually see is that the galvanometer would then be deflected in an opposite direction. So then it would point opposite to what it was initially pointing towards. So the galvanometer points in opposite direction. When magnet is moved away from the coil. So what we see here is that when there is some relative movement between the magnet and the coil, then we have some deflection on the galvanometer, right? So then there is some current which is flowing throughout the coil. So what we just saw with the magnet moving towards the coil is also something we would see, that if the coil was moved with the magnet stationary. In that case as well, we would have deflections on the galvanometer. And even if we take this bar magnet here and if we place this inside the coil, even in that case we would have no deflection on the galvanometer. So what we end up concluding is that only when there is some relative motion, so when there is relative motion between the coil and the magnet, is when the galvanometer deflects. So it should also be kept in mind here that the galvanometer just shows the presence of current, and this is some induced current. But we know that what induced current flows actually only flows because there is a complete path for the current to flow. So what is actually induced here in this circuit is an EMF. And what this relative movement then shows us is that there is only an EMF which is being induced when there is some, when the lines of magnetic flux are being cut. So what we end up concluding is that the EMF is induced when these lines of flux, or what we previously used to refer as the field lines, are cut. Additionally, if you just do the same experiment with slightly different movement, you get some more observations, which is that the magnitude of the EMF increases as and this is a number of factors that we are about to discuss now. So this increases, first of all, if the speed of relative motion increases. So why am I saying relative motion? Is basically to make you understand that it doesn't depend on the coil moving or the magnet moving, as long as they are both moving with respect to each other. So they are either moving towards or either moving away from one another. So basically the distance between them must be varying in some way. So it also increases if the number of turns on the coil increase. So if you think about both of these together, if you increase the speed at which this relative motion occurs, that just means that the lines of flux are now being cut more rapidly. And if the number of turns increase, well, for the number of turns in the last video we saw a term, right? It was called the magnetic flux linkage. So Faraday actually observed exactly what we are observing now, although the experimental setup was slightly different for him. And what he said basically was this. So we're now talking about Faraday's law of electromagnetic induction. So what he said was that the induced EMF is basically proportional to the rate of change of magnetic flux linkage. Writing this in an equation form, that means that if I call the EMF, the induced EMF, some epsilon, so that is proportional to the change in the magnetic flux. But since this is rate of change, so it's with respect to time, so it's over some time through which the magnetic flux linkage changes. For reasons we won't go into because of the scope of the syllabus, here the constant of proportionality is basically 1. So what this really says is that the EMF is equal to the rate of change of magnetic flux linkage. So let's have a look at a few examples to see the use of this equation. So actually we'll have a look at the examples in the next video. Right now let's look at something else, which is if you are dropping a bar magnet through a coil. So basically we are having a bar magnet which will go through a coil, and from the coil we'll have a data logger attached which will basically record the induced EMF. So a coil with n number of turns, and these coils, the individual coils are very close together. So the magnet, as you can see, the dimensions of that are much larger compared to the dimensions of the coil itself. So to the coil is connected a data logger, and it's measuring the EMF induced at very small intervals of time. So as the magnet is dropped from some height, so we can see that as the magnet would speed up while it's falling, so then it would have a magnetic field of itself, and then when the magnetic field lines will basically be cut by the coil, there will be an EMF induced through here. So when the coil is moving downwards, so it's moving towards the coil, then some EMF would be induced. But when it's moving outwards, so basically when it's moving away from the coil, then an opposite EMF would be induced. This information is shown in this graph. So the actual graph actually has much more detail than what we just talked about. So here let's say this AB section is when the magnet is entering the coil, and this section, which is BC, is for the magnet leaving the coil. So as the magnet was moving, first the induced EMF was increasing because of the acceleration due to gravity, the speed is increasing. So the magnetic field lines or the lines of flux are being cut at a faster rate, leading to an induced EMF. But then as the magnet is at a position like this, so maybe where it's midway, then it actually starts leaving the coil. So in a position like that, what would happen is that the field lines, or rather the magnetic flux linkage, would start decreasing as there are less field lines which are passing through the coil, which are being cut by the coil. So then the induced EMF starts decreasing. And then you can also see that the induced EMF is negative over this section BC. And this is exactly the idea that we just talked about, that when the magnet is leaving the coil, so the flux linkage would decrease and the EMF induced would be in an opposite direction. You can also see here that the maximum induced EMF is less in the positive direction and is more in the negative direction, and this is basically because of acceleration due to gravity. So when it's moving outwards, it would be moving faster, and it would be cutting, the coil would be cutting the field lines at a greater rate. So it's moving faster, and hence cutting more field lines. Right, so there is a greater rate of change of magnetic flux linkage here. So the coil is cutting more field lines, leading to a greater EMF. So we know this equation, that the EMF is delta n phi over delta t. Now usually n does not change because this is the number of turns. So instead, if we write it like this, delta n and phi is BA over delta t. So what usually changes is either the magnetic flux density or the area. So we can also write this as n delta BA over delta t. Now this is n delta phi basically. So rearranging, we can also see that this equation can also be written as the induced EMF times delta t would equal N delta phi. So E delta t would basically be the area under a certain slice of the graph where the time interval is delta t. So that gives us the magnetic flux linkage here. So the area under an EMF time graph is the magnetic flux linkage. So that's the area under a ET graph.